Every calendar year, global industrial facilities are manufacturing upwards of 430 million metric tons of synthetic polymers. To visualize the staggering scale of this output, imagine a continuous line of freight trains laden with plastic that could encircle the entire planet 7 times over. Perhaps even more unsettling is a statistic that few outside the professional industry truly grasp. Less than 10% of all the plastic ever produced has actually undergone a successful recycling process. The overwhelming majority of this material eventually occupies landfills, saturates our oceans, and increasingly permeates our very biology. Recent scientific inquiries have confirmed the presence of microscopic plastic particles within human blood, lung tissues, and arterial walls. In just 1 century, a material that revolutionized modern life has begun to accumulate within the human body itself. However, in October of 2025, a research team from a forestry university in northeastern China released a scientific paper that has captured the attention of the global engineering community. They reported the successful creation of a fundamentally new category of material, a structural polymer derived entirely from bamboo. This is not a composite of bamboo and oil-based resins. It is a 100% bamboo-derived substance that demonstrates mechanical strength superior to many conventional plastics. It remains compatible with existing industrial machinery, and most importantly, it can undergo complete biodegradation in standard soil within a window of just 50 days. Understanding the magnitude of this breakthrough requires an objective look at why the global economy is so inextricably tied to synthetic plastics. Consider the devices in our pockets, the containers preserving our food, the hardware housing our computers, and the interior components of our transportation systems. They all rely on plastic because it possesses a unique combination of physical properties that few other materials can emulate. It can be liquefied and molded into virtually any geometric configuration, from a simple bottle to a high-precision medical component. The manufacturing cost is remarkably low, and the material is inherently resistant to the forces of rust, rot, and fracture. It is a nearly perfect insulator and remains durable through extreme weather conditions and physical stress. In the healthcare sector, the reliance on these polymers is absolute. Every sterile syringe, every intravenous fluid bag, and the protective wrappers ensuring the sterility of surgical instruments depend on the reliability of modern plastics. The global food supply chain is equally dependent. Plastic barriers extend the shelf life of produce and ensure that essential nutrients can be transported across continents without contamination. Therefore, when policymakers suggest an immediate departure from plastic use, the fundamental industrial question remains: what other material can provide this level of utility while remaining economically viable? The very characteristics that make plastic an industrial miracle are the same factors that render it an environmental and biological hazard. Its durability is a double-edged sword. It is designed to last indefinitely, which means a single discarded bottle will likely persist in a landfill for centuries. It does not disappear. It merely fragments into increasingly smaller particles, microplastics, that eventually enter the global water supply and the agricultural soil. We are now seeing the biological consequences as these particles are consumed by marine life, avian species, and ultimately humans. The material foundation of the modern world is now a part of our internal biology, and the long-term clinical implications are still being mapped by the scientific community. This has placed the world in a precarious position where we remain dependent on a material that has no natural exit strategy. For decades, the bioplastics industry has attempted to solve this dilemma, yet nearly every previous alternative has hit a definitive technical wall. Most bio-based materials either lack sufficient mechanical strength, fail to biodegrade outside of industrial facilities, or are simply too expensive to produce at a scale that could influence global markets. The most prominent example of a failed alternative is polylactic acid, or PLA. While it is derived from fermented cornstarch and is technically compostable, it requires a specialized industrial facility maintained at extreme temperatures to actually break down. If a PLA component ends up in a standard landfill or a natural environment, it remains as persistent as traditional plastic. Furthermore, using edible corn to produce plastic creates an ethical and economic conflict between energy needs and the global food supply. Another alternative, known as PHA, offers better biodegradation but involves a complex bacterial fermentation process that makes it several times more expensive than petroleum-based polymers. Starch-based plastics suffer from a catastrophic lack of water resistance, rendering them useless for many practical applications. Cellulose acetate, while strong, often requires harsh chemical processing that negates its environmental benefits. The core challenge was never a lack of creativity. It was a fundamental problem of molecular chemistry at the deepest level. Until now, no one had figured out how to re-engineer a plant's structural building blocks into a plastic-like material without relying on synthetic adhesives that ruin the environmental objective. The solution finally emerged from an unexpected source, the Northeast Forestry University in Harbin, China. Rather than a petrochemical giant or a high-funded Silicon Valley startup, this innovation was pioneered by researchers Haiping Wu and Dawei Zhao, specialists in forest science. They focused their efforts on bamboo, a plant known for its incredible growth rate and structural resilience. The primary structural component of bamboo is cellulose, a molecule held together by incredibly powerful hydrogen bonds. These bonds allow bamboo to withstand immense stress in nature, but they also make the material difficult to reshape. In the past, scientists tried to create bamboo-based plastics by mixing ground fibers with traditional plastic glues, resulting in a hybrid material that still contained oil-based toxins and failed to biodegrade. The team in Harbin, however, bypassed this compromise entirely. They developed a two-step chemical process that does not mix bamboo with plastic, but actually transforms the bamboo itself into a structural polymer. In the first stage of this process, the bamboo cellulose is treated with a specialized liquid solution consisting of zinc chloride and formic acid. This solution is specifically engineered to untie the strong hydrogen bonds without damaging the integrity of the cellulose molecules themselves. It is a process of precision disassembly, allowing the material to become flexible and moldable without losing its inherent strength. In the second stage, the researchers introduce ethanol, which acts as a molecular architect. It guides the loosened cellulose molecules to reconnect in a completely new configuration, creating bonds that are even more robust than those found in the original plant. The resulting substance, termed bamboo molecular plastic, or BM plastic, possesses the physical characteristics of a high-grade synthetic polymer, but remains 100% derived from the bamboo's original molecular structure. No synthetic resins or petroleum-based additives are required, and the entire process leaves behind no hazardous chemical waste. When the engineering community analyzed the performance metrics of this new material, the results were statistically significant. In standardized strength tests, BM plastic demonstrated a tensile strength of 110 megapascals. To put that into perspective, this is approximately double the strength of standard corn-based bioplastics and even surpasses high-impact polystyrene, a material commonly used in consumer electronics and industrial components. These figures place the material within the mechanical range of certain aluminum and steel alloys used in the automotive and aerospace sectors. It is not merely a green alternative. It is a high-performance structural material capable of sustaining significant loads without warping or failure. In bending tests, it outperformed tough ABS plastics, the same durable material used in automotive dashboards and high-stress industrial parts. The thermal stability of the material is equally impressive, maintaining its structural integrity at temperatures exceeding 180 degrees Celsius. Researchers subjected samples to intense heat for 7 consecutive days, and observed zero signs of cracking or deformation. The material also exhibits a high work of fracture, meaning it can absorb a significant amount of energy before failing, which is a critical requirement for automotive safety components and consumer electronics. Finally, the most anticipated result was the biodegradation data. BM plastic underwent complete decomposition in regular soil in approximately 50 days, requiring no industrial composting facilities or special conditions. It simply returns to the earth like any other organic matter. The economic viability of any new material is often determined not just by its initial strength, but by its performance across a full life cycle. And it is here that the data on bamboo molecular plastic becomes particularly compelling for industrial analysts. One of the most persistent failures of traditional synthetic polymers is the phenomenon of downcycling. Every time a standard plastic bottle or container is processed for reuse, the molecular chains are fractured and weakened, resulting in a material that is less durable than the original. This is why most recycled plastic is relegated to low-value products like park benches or industrial carpeting. However, the chemical process used to create this new bamboo-derived material appears to circumvent this limitation. Because the material is held together by a specifically engineered molecular architecture rather than simple physical bonds, it can be dissolved and reformed while maintaining nearly 90% of its original mechanical strength. This suggests the possibility of a truly circular economy for structural materials, where a product can be recycled indefinitely without a significant loss in performance. The research team behind this breakthrough opted for total transparency, publishing their full datasets and methodological frameworks in major peer-reviewed journals like Nature Communications. By inviting the global scientific community to scrutinize their findings, they have established a level of technical credibility that is often missing from corporate-backed material science. The selection of bamboo as the primary feedstock for this transition is a decision rooted in both botanical science and strategic logistics. To appreciate the scale of this advantage, one must look at the unique regenerative properties of the bamboo plant. Unlike traditional timber or agricultural crops, bamboo is a rhizome-driven system. Once a forest is established, it requires no replanting, no industrial fertilizers, and no specialized irrigation systems. Some species are capable of growing over 1 meter in a single 24-hour period, a biological rate of production that is unmatched by any other plant on Earth. While a standard pine forest requires 25 to 30 years to reach harvestable maturity, a bamboo grove can be fully harvested every 3 to 5 years. From a land use perspective, this efficiency is critical. Bamboo produces approximately 5 times more biomass per hectare than traditional timber forests and sequesters carbon at a significantly higher rate. Furthermore, bamboo thrives on marginal land that is unsuitable for traditional food crops. This effectively solves the ethical dilemma that has plagued corn-based bioplastics, which are often criticized for diverting valuable farmland away from the global food supply. By utilizing a non-food resource that grows on rugged terrain, the industry can scale production without threatening food security. The logistical foundation for this transition is already remarkably mature. China currently manages over 7.5 million hectares of bamboo forests, encompassing more than 500 distinct species. The existing bamboo industry already contributes hundreds of billions to the national economy and provides a livelihood for millions of rural workers. This means that the infrastructure for harvesting, transporting, and primary processing is already functioning at a massive industrial scale. For a global manufacturer, this is a decisive factor. They do not need to build a supply chain from the ground up. This pre-existing infrastructure significantly lowers the barrier to entry and allows for a rapid transition from laboratory innovation to global distribution. Many advanced materials fail not because the science is flawed, but because the raw material supply is too rare or geographically isolated to meet global demand. Bamboo, however, is a ubiquitous resource across Asia, Africa, and South America, with over 22 million hectares of forest globally. It is a resource that is already being harvested for construction, textiles, and paper, meaning the shift toward the bamboo-based plastic is an evolution of an existing industry rather than the creation of a new one from scratch. Beyond the raw material advantage, the most significant barrier to the adoption of bioplastics has traditionally been the requirement for specialized manufacturing equipment. Most sustainable alternatives require a total overhaul of existing factory lines, necessitating massive capital expenditures that most companies are unwilling to risk. This new bamboo molecular plastic appears to bypass this hurdle entirely. The material has been successfully tested on standard injection molding machines, which are the foundational tools of the global plastic industry. It can be processed, drilled, and shaped using the exact same hardware that currently produces billions of petroleum-based products. To demonstrate this compatibility, researchers have already manufactured a wide array of functional prototypes, from industrial gears and shipping containers to intricate decorative items, all using unmodified factory equipment. This means a manufacturer could potentially switch from petroleum-based polymers to bamboo-based materials almost overnight without investing millions in new machinery. Furthermore, the energy profile of this manufacturing process offers a significant operational advantage. Traditional plastic production is a high-heat industry, requiring massive industrial ovens and pressurized tanks to melt and form synthetic resins. The bamboo molecular process, by contrast, operates primarily at room temperature. By eliminating the need for constant high heat cycles, factories can achieve a drastic reduction in their energy consumption and overall carbon footprint. The chemical catalysts used in the process, zinc chloride and formic acid, are abundant and inexpensive, and the ethanol used as a guide can be recovered and reused within the system. This creates a production model that is not only more sustainable, but also inherently more cost-effective from an energy perspective. The current economic analysis places the production cost of this bamboo material at approximately $2,300 per metric ton. While this is nearly double the $1,200 cost of standard petroleum-based plastic, the gap is narrowing rapidly. First, as production scales and efficiency improves, the unit cost is projected to decline significantly. Second, the true cost of petroleum plastic is increasingly being scrutinized through the lens of externalized liabilities. When the costs of environmental remediation, microplastic health impacts, and new carbon taxes are integrated into the equation, the real economic burden of traditional plastic is estimated to reach $2,400 per ton by the end of the next decade. In this context, a material that is currently viewed as a premium alternative may soon be recognized as the most fiscally responsible choice. The strategic response to this technology has been swift and coordinated. As early as 2022, national initiatives were launched to accelerate the replacement of plastic with bamboo alternatives. By 2023, these plans had evolved into a multi-year industrial mandate. We are already seeing the results in the global market, with exports of bamboo-based structural materials rising significantly. High-durability bamboo pipes are being deployed in urban infrastructure to replace traditional steel and concrete, and the material has even been successfully utilized in the aerospace sector, where a bamboo-reinforced drone demonstrated a 20% weight reduction and a 75% cost saving compared to carbon fiber. The global conversation surrounding plastic waste has reached a stalemate in international diplomacy, as nations struggle to agree on production limits. However, the emergence of a high-performance, cost-effective alternative changes the fundamental dynamic of this debate. The most effective way to end a dependency is not through regulation alone, but by providing a superior technology. While there are still challenges to overcome, particularly in developing flexible versions of the material for packaging and films, the structural capabilities of bamboo molecular plastic are undeniable. We are witnessing a transition from a century of oil-based extraction to a new era of plant-based manufacturing. This is not just a story about sustainability. It is a story about the next industrial pivot. For the first time, a material offers the performance that the global economy demands without the environmental debt that the planet can no longer afford. The future of the industry is no longer found in the oil well, but in the rapid growth of the bamboo forest, as a 100-year reliance on synthetic polymers begins its inevitable decline.